Chapter 14, Sample Problem Number 11. A string is stretched so it is under tension and tied at both ends so the endpoints don't move. Mechanical oscillator then vibrates the string so a standing wave is created. The dark line in each diagram represents a snapshot of a string at an instant in time when the amplitude of the standing wave is at a maximum. The lighter lines represent the string at other times during a complete cycle. All of the strings are identical except for their lengths and all have the same tension. The number of nodes and antinodes in each standing wave is different. The length of the strings, L, and the amplitudes at the antinodes, A, are given for each figure. And we are looking to rank the frequencies of the waves. So let's go highlight some of the important stuff that we know. Most importantly, the strings have the same tension and they are identical, which means they have the same linear density, which means together that they all have the same speed v. So they're all the same velocities. And then we know we're in a standing wave pattern, so that our fundamental mode for strings at both ends, the fundamental mode, looks like this. So let's figure out what mode we're in for each of them. In case A, we have one copy, and then two copies, 3, 4, 5. So this is n equals 5. And in case B, we have 1, 2, 3, 4, 5, 6, 7 copies of the fundamental, so this is n equals 7. And here we have 1, 2, 3, or n equals 3, because there are 3 copies of the fundamental. And then finally, here we have 1, 2, 3, 4. This is n equals 4. And that would be great if they were all the same length. We could very easily answer this, but sadly we really can't. So we need to figure out what the fundamentals are for each of these in terms of the same speeds, or at least how they relate to each other. For all waves that are a fixed string, something with the nodes at each end, we know that the fundamental is the velocity over 2L, and that all others are just n times that velocity. So we want to figure out what that is in each of these cases. And for convenience, well, there's not going to be any really convenient thing here. We know the amplitudes aren't going to be important, so I'm going to ignore them, but we need to figure out the fundamentals of A, B, C, D, etc. So, well, we're just going to have to, we'll treat V over 2 as the same for all of them, and so maybe we should make a little chart. Yeah, let's make a little chart. It might be the smarter way to do this. So let's get rid of this for now and go back and say we're going to have case A, B, C, D. We're going to figure out what, we're going to figure out, we have the length, so we're going to figure out the frequency of the base mode. We have the number, and so we're going to figure out our actual frequency that we want. And for case A, our length was 25, so our frequency is going to be V over 2 times 25, and I'm going to write that as just 1 over 25 times the other stuff. And then, but my mode is n, so my actual frequency becomes 1 over 5th of some multiple. For B, we have that the length is 28, so the frequency would be 1/28 of V over 2L, of V over 2, and then, but our mode is 7, so this is now 7/28 is our frequency. For case C, the length was given as 27, so our frequency is V over 2 times 1 over 27, but we have mode 3, so this is 3/27. And then finally, we have, again, 28, so 1 over 28, but the mode was 4, so this is now 4 over 28. And maybe the smart thing is to just get decimal equivalents for all of those. So 4 over 28 is 0.1429. And 3 over 27 is, of course, 0.1111. And 7 over 28 is, of course, just 0.25. And 1 over 5 is 0.20, etc. So this seems to indicate that we would have the highest frequency would be B, the next highest would be A, then D, then C. In retrospect, that was way more complicated than it needed to be, so I'm going to do a simpler case. This is all fine, true, but we can actually clean this up and do it, sadly, much faster than that. So let's clean up. And we're going to come back. We're still going to use it. The speed is the same. And I'm going to remember that the speed is always is lambda over t, or lambda times f. If the speed is the same, the larger we get in lambda, the less we have in f. So we're really just looking for what the wavelengths are. And the wavelengths are pretty easy to find here. This is one wavelength, which if we look at it, we have 5 of them in 25 meters. Or we have 2.5 wavelengths in 25 centimeters, so that's 10 centimeters wavelength. And then here we have, this is 1, and we have 3.5 in 28 centimeters. So our lambda is 28 over 3.5, which is 8. And then here we have 1.5 in 27. So 27 over 1.5, there's 18 centimeters per. And then finally here we have 2 of them in 28, so that's 14. So now we can say that the shorter wavelength is the highest frequency. So our shortest wavelength is B, and then our next shortest wavelength is A, and then D, and then C. And we're in the same place. You can actually sort of just eyeball that it's A, and then B, and then D, and then C in terms of shortness of wavelengths. And therefore the frequency would be the opposite way. So there we go.